Okay, everybody, this is video 2, and I'm just going to go through the answers. I just thought it would be better to do it verbally rather than just write them down. So let's go through the other answers here. Number 4, the question was just asking what are the hypotheses here, and so this one is talking about scores ranging from 0 to 200. Now this is a little bit interesting because this is definitely one having to do with means, because the null hypothesis is, it says the teacher suspects that older students have a better attitudes towards school on average. So 115 is what's normal for college students, and the teacher suspects that older students have, like their older students would have a better attitude. So in this one, the null hypothesis would be that the mean score for that college, for the older students, is equal to 115. That's the null, and the alternative hypothesis is that the mean is greater than 115. And then over here in number 10, it keeps going, and so they actually got a sample mean of 125, which is a lot bigger than 115. Sample standard deviation was that a significance test yields a p-value of 0.0101, so a really small p-value. It's lower than our 0.05 that we usually use. What would it mean for the null hypothesis to be true in this setting? For the null hypothesis to be true, that would mean that the older students at their college are just the same as the average for everybody else, because the null is that nobody's any different, that nobody's higher than anybody else. Everything's the same with the null hypothesis, and so we just assume these students are just like everybody else. The alternative is that they have better attitudes about school. The p-value in this case is the probability of getting results like we got or more extreme if the older students at our school are just like everybody else and also have a mean of 115. The probability of getting results like this, if that's true, is 0.01. There was like a 1% chance that you could get a 125.7 for your average doing a study this way, when the real average is only 115. Like 115 is the normal average, and we got a 125.7. What are the odds of getting an average that's that much higher? Well, the odds are, it's a 1% chance. Okay. All right, next to 20 and 21, if I remember correctly. Go next page. Here we go. 20 and 21. Okay, student performs test of null, mu equals 12. So this is again about means, of the mean being 12 versus the mu being not 12 at the 0.05, and they get a p-value of 0.01. So the probability of getting results like we could have got, like we got, or more extreme, if the null is true, if the mean is just 12, is 0.01. You've got a 0.01 chance of getting a result that different, whatever the answer was. They said because the p-value is small, we reject HO. That's true. If your p-value is really small, then the probability of getting results like this, if the null was true, is really small. It's like, wow, that's a really weird thing to happen if the null was true. And so we reject the null. And so, good so far. The data prove that the alternative is true. Wow, it doesn't prove it. It says we've got convincing evidence that it's true, but it doesn't prove it like you would think with like a geometry proof or a math proof. It just says there's really convincing evidence, so we're going to reject the null, and we're going to go with the alternative hypothesis. But it's still just on the basis of evidence. It's not a proof. Number 21, heavy bread. The mean weight of loaves of bread, 1 pound. You are supervisor of quality control at the bakery. You are concerned that the loaves are too light. You weigh a simple random sample and you find the mean weight is 0.975. What would be appropriate hypotheses for a significance test? So we're going to be doing it for the mean, and the null hypothesis is that the mean is 1 pound, and the alternative hypothesis is that the mean is less than 1 pound. Because you notice it says you are concerned that new employees are producing loaves that are too light. So you think the real average is smaller than 1 pound. And so you're going to get you're going to get a sample and see if it's strong enough evidence to conclude that. The parameter would be the mu, the mean, which is the true weight of loaves loaves that we are producing at this time. Explain why there's some evidence. Well, there's some evidence because they got a 0.975. So, that's less than 1. Like, it's supposed to be average 1 pound. They got 0.975, which is less than 1. So that's some evidence. It's just, is it enough evidence to discount there's just random variation? Let's find out. The p-value for this test is 0.0806. Interpret the p-value. Okay, there's a probability that, and then you should be able to say the rest. Give you a second. Did you say the rest? Here we go. There's a probability. If you have to back it up and hear this again, make sure you hear it twice. There's the probability of getting results like we got, getting 0.975, or even more extreme. Because when we do probability with a normal model, we keep going. The probability of getting results like we got, or more extreme, if the null is true, is 0.08. There was an 8% chance, just by random luck, of getting results like we got, or even worse, even lower. So it could happen just by random luck. It's an 8% chance. It's pretty unlikely, but it could happen. What conclusion would you make at the alpha equals 0.01 significance level? You'd fail to reject the null. Well, it's lower, but it's not convincingly lower. It's not convincing evidence. It's not statistically significant evidence. It's lower, but not lower enough for me to be sure about it. I'm not going to fire people over it or something. All right, I remember 24 was one. Television networks rely heavily on ratings of TV shows blah, 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 blah. Suppose a network has decided that Miniature Golf with the Stars, that's awesome, will only be renewed if it can be established that more than 12% of U.S. adults watch the show. Wow, that's a lot of adults. Okay, just because there's so many things to watch, right? So I feel like that's kind of high. But anyway, all right. A polling company asks a random sample of 2,000 adults if they watch this show, and they're going to do a test, and they're going to do this test where P is the true proportion. This is all the setup for hypothesis tests to find out if we have statistically significant evidence. But that's not what the question's asking. The question's asking what would be a type 1 error and a type 2 error and a possible consequence. Okay, when I'm doing a type 1 and type 2 error problems, I often start off by stating the basics of what it is, and then I put in the context. So I say, all right, type 1 error, the null is true, but we think it's false. I just have that memorized. Type 1, the null is true, we think it's false. Why would we think the null is false if it's true? Well, because the data, maybe it's far enough away just by random chance, and it happens to be far enough away that we conclude that it's false when really it was just weird data. And that's what it's like. Quirky random data is what a type 1 error is about. So what is it in this situation? In this situation, the null is true. So that means 12% of people are watching the show, but we think it's false, but we think the alternative is true. So we just happen to get a weird blip, and we happen to get 18% based on our random sample, when really it's only 12%. That would be a type 1 error. If it was high enough that we concluded, oh, wow, the show's working. And what would be the consequence? The consequence is we renew the show. And then as time goes on, we realize, oh, there aren't that many people watching it. We had kind of a weird blip that night. And we happen to get a little bit higher than what's real. So type 1 error, we renew the show and it loses money, or it doesn't make us enough money. Type 2 error, the null is false, but we're not convinced. Like, it actually is high. Well, I'll say in this case, it actually is over 12%. So maybe we got like 14%. But when we did the statistical analysis, we said, boy, that could easily just be random luck. So we're not convinced by the evidence. And so we fail to reject the null as a result. The consequence there is that we conclude that, our best guess is that the show is still at 12%. Which it actually is wrong. And so we don't renew it, and we lose an opportunity to make money because the show would have been a hit. That's a classic kind of problem for describing type 1 and type 2 errors, and then what are the consequences for them. Okay, at 10 minutes, I got a little more time. So let me just check, make sure I'm doing this right. Yeah, 24, 26, 27. Okay, we'll take a look at those, and then we're going to be done, I think. All right, 26. EPA has determined safe drinking water should contain 1.3. Okay, they're going to do a significance test by doing 30 random samples. Okay, cool. Or a random sample of 30, n equals 30. That's great. And then the null is that the mean is still 1.3, no change. The alternative is that mean is greater than 1.3, and so meaning that there actually is too much copper. Type 1 error. Null is true. I think it's false. Null is true. Type 1 error is that it's actually 1.3 is correct, and it's at 1.3 milligrams per liter. But because of a weird sample, we think that it's actually higher, and so we think that that there's toxic issues here. Type 2 is the null is false, but we can't notice it. We don't notice it because it's not extreme enough. We fail to reject it because it's not conclusive. So that would be that the null is false and it's not 1.3. It's actually greater than 1.3, but we don't notice it. Which type of error is more serious? Man, a type 2 error, because then people are still going to get poisoned because we're going to say, oh, it's not convincing, looks like it's okay, and really people are going to be getting too much copper and it's going to be poisoning people. Yikes. Based on your answer, do you agree with the company's choice of alpha equals 0.05? So that's the thing, is that you can adjust the alpha if one error is worse. So type 1, we want to make it really, really, really easy to reject the null here. Because if there's any sign that people could be getting poisoned, then we want to do something about it, right? And so we would want to go with an alpha that would be as, just make sure because I'm not writing anything down, I have to think about it for a moment. We want to go with an alpha. We want to reject the null if it's all. We make it as easy as possible to reject the null if it's actually false. And so we would like an alpha of 0.1. Go with a bigger alpha, because with a bigger alpha, then there are a lot more numbers, a lot more results that are going to cause you to reject the null. And I'd rather reject the null here, because the worst thing that could happen is that I failed to reject the null when it was actually false. The worst thing that could happen is that the average is above 1.3, and I just don't, like we get a data result of like 1.4, and we go, oh, 1.4, that's not convincing enough, when really it's like, oh, people are being poisoned here. So we want to make it very easy to reject the null if the null is false. And so let's make alpha as big as possible. Make it 0.1. That's about as big as anybody goes. Okay, last one, 27, right? 27. I mean, I know there's more, but the video's going to run out of time. 27. Oh, yeah, this one. I saw this one. When I signed it. In the population of people in the United States, about 10% are left-handed. And so Simon wonders if more than 10% of people. And so he finds that 16% in his sample. And so he's like, well, what are the odds of that happening just by random chance? So what he does is he sets it up, this simulation, where each student has a 10% chance of being left-handed. So 10%, he set it up ahead of time that 10% is the actual proportion in this simulation, and said, what if the actual number was 10%, and then you did a random sample and you got 16%. What are the odds of that happening just randomly, like where the population is at 10%, but you just happen to get a weird sample and you happen to be at 16%. What are the odds of that happening? Well, so we can kind of look at this and we can see, like, for all of these data points out here, even though he said it at, Simon. He said it at 10%, but just by random chance, sometimes he got 16%, sometimes he got 18, sometimes he got 20, sometimes he got 22. It was pretty infrequent, but a couple times he got 22%. So all these ones represent times where you got 16% or more, despite the fact that you set it at 10%. State the appropriate hypotheses. Am I good? Yeah. Null. I'm not gonna make it. Oh well. But the null is 10%. P equals 10%. Alternative P is greater than 10%. Use the simulation results. What you want to do is you want to figure out how many of the 200 trials were out here, and then figure out what the proportion is. That is your P value. Oh, I'm out of time. Sorry, it's going to cut off.